Hello everyone, welcome for the first joint astronomy colloquium of this semester. It's a real honor to welcome Cathie Clarke here from the Institute of Astronomy at the University of Cambridge. Cathie got her PhD from Cambridge, then did a postdoc at the University of Santa Cruz, and came back to Cambridge as an advanced fellow and had 1 year at Queen Mary's. After that, she returned to Cambridge as a lecturer and is now a full professor there. And Cathie last year won the Eddington Medal of the Royal Astronomical Society for her work on protoplanetary disk evolution and photoevaporation, which she will be talking to us about today. So Cathie, I'm looking forward to your talk.
Thank you. Well, it's a great pleasure. No, it's a real pleasure to be in this great astronomical hub here in Heidelberg with so many people working on disks and star formation. What I'll be telling you about this afternoon is indeed the dispersal of protoplanetary disks, and I'm going to come straight to the point by showing you a plot of dust mass around stars as measured in the millimeter as a function of stellar age, stars of different spectral types. And what you'll notice is that beyond about 10 megayears, the amount of detectable dust has gone down by several orders of magnitude relative to what it was previously. So the older systems are known as debris disks, and it's not just a semantic distinction between them and protoplanetary disks, because as you can see from looking at the quantities of dust here, there is still in the protoplanetary disk phase, during the first few million years, enough material in dusty form to go on and make substantial quantities of rocky planets. And if I showed you equivalent plots for the gas, you would come to a similar conclusion. So it's a rather simple thing, apparently, that for a matter of a few million years you have protoplanetary disks. Something happens, we don't know what. The quantities of detectable material go down dramatically, and the main body of planet formation is over, apart from maybe some assembly of planetesimals, which obviously aren't detected at millimeter wavelengths. So what we'd like to know when we look at a plot like this is that what's going on? Is it simply a case that disks are self-consumed by forming planets, or is it that there are extrinsic dispersal processes and that planet formation is carrying on an environment where it has to contend with some competitive process dispersing the disk? So that's the kind of motivation here. So spend about the first third of the talk talking a bit about disk diagnostics and what clues they might give you as to what's going on as a clearing mechanism. There's been a lot of work done over the years on what's called internal photoevaporation, so that is where the source of the X-ray and ultraviolet radiation is from the central star. And I'll be telling you a little bit about what we can say about this from an analytic perspective and why I think it's not yet a done deal in terms of really knowing what's going on there. And then quite a lot in the last third of the talk talking about external photoevaporation, which is essentially far ultraviolet radiation from adjoining OB stars in clusters. And thinking about environmental effects, I'm going to be tensioning how much, what the influence of external photoevaporation is against the effect of stellar encounters in dense environments. And particularly in this latter work, there are three characters who have really helped to transform this latter field. Stefano Facchini was a former PhD student, now an ESO fellow. Tom Howarth, a former postdoc, now at Imperial. And Andrew Winter, still a PhD student who's visiting here for 2 months. And many of you, I hope, will have the chance to talk to him while he's here. So I think for anybody who lives and works outside the bubble of protoplanetary disks, you'll be aware that this is a golden era for characterizing protoplanetary disks with ALMA. Just last week came out a nice survey at intermediate resolution, about 15 AU resolution of disks in the Taurus star-forming region, showing a zoo of interesting structures and gaps. Probably, if we had the lights down further, we'd see it better, but no need for that. I really wanted to draw your attention to the asterisk one there, CI tau, where we recently published data which was at 3 times higher resolution. So if you see the panel on the right, you don't really need to turn the lights down to be able to see the very clear structure in this disk. This beam here is about 5 AU. And why we're very excited about this is that CI tau was the first star in which a hot Jupiter had been known to exist in a protoplanetary disk. You know, there's a lot of controversy as to when hot Jupiters arrive close to their parent stars, but here we've got a 2 million year old star which has got a hot Jupiter. Needless to say, this was not discovered by ALMA, the hot Jupiter, But, thank you, the point of the ALMA discovery is to say that, as has been found amongst mature hot Jupiter systems, there seems to be a preference for hot Jupiters to have friends. There are a number of papers called Friends of Hot Jupiters, meaning other gas giant planets further out. And here we've got some subjovian gas giants located at about 10 and 40 and 100 AU in this disk. So all this is extremely exciting. That's been, that sort of thing has been very much the topic of my ERC grant, which is coming to an end. But I could point, it's in that white blob there, right? So it's 0.1 AU, the separation of the hot Jupiter, and the beam's 5 AU, so we definitely don't see the hot Jupiter in the ALMA image. It was a radial velocity discovery, the hot Jupiter. But if you wanted me to point at the other three, it's each of those dark lanes can be interpreted in having an orbiting planet there. So the reason why I'm not giving a colloquium on this is I think it's slightly premature, because at the end of this year, the ALMA Large program by Sean Andrews will be coming out, in which they'll have a number of such disks at comparable resolution to our image on the right. Not ones with hot Jupiters, but nevertheless we'll get a much more complete sense statistically of dust distributions and small-scale structure. So very, very exciting times for disk physics. But images like this don't tell you too much about disk dispersal, because what you really want to, when you're thinking about disk dispersal, is to be able to measure flows of gas out of the disk. And the most obvious flow out of a protoplanetary disk is simply its accretion onto the star in the middle. I think it was Lyndon Bell and Pringle in 1974 who first of all suggested that protoplanetary disks were another form of accretion disk, as is found in other astronomical contexts like cataclysmic variables and disks around quasars. And over the years, this has become the standard interpretation of measuring the Balmer lines from the accretion funnels and from ultraviolet excess on the star. And here, Lee Hartman, quite a few years ago, has assembled data on accretion rates onto stars as a function of stellar age, showing that the accretion rate onto the star falls away with time, and he's fitted various self-similar viscous accretion models through there. The point I want to make about this is that we cannot forget about accretion. The accretion rates are always such that if you take a disk and you measure its mass and you divide it by its accretion rate, you get a number which is roughly the age it is now. So it's always a significant player in shifting material around in the disk. But that isn't the answer to what produced that diagram I showed you on the first slide. Because if you just run viscous accretion disk models forward in time and ask how long do you have to wait before you, say, become optically thin at 2 microns so you don't detect any evidence of a dust disk around it, you'd have to wait hundreds of millions of years, well into the debris disk phase. So they may be behaving as accretion disks in some sense, but this is not going on forever. We need some other process to disperse it in addition to that. Now, of course, the celebrated thing about young stars is they have vigorous outflows and jets, which are some of the most photogenic objects known in astronomy. They tend to be more active in the younger evolutionary phases. So here are a couple of celebrated jet and outflow sources, which are respectively class 1 and class 0 protostars. So they're at an earlier evolutionary stage. They're probably less than 1 million years old. So they are not at the stage that we're considering here, where the disk is being dispersed. And another way you can see that is that in the plot on the right, recent compilation of the accretion rate onto the star and the mass loss rate in the jet, and showing that as your accretion rate goes down, which as we've seen is broadly speaking a function of time, the mass loss rate in the jet goes down. And the canonical number on that is that the ratio of the two is of order 10%. So this tells you this can't be the main thing which is dispersing your disk, because you've already seen that accretion on its own isn't enough, and apparently the jet loss rate is only about 10% of that. So there are a few reasons why photoevaporation is, in principle, quite a promising way of getting rid of disks. First of all, to state the obvious, a young star, the potential is pretty shallow, certainly compared with around a compact object like a neutron star or a white dwarf. So if you heat with ultraviolet or X-ray radiation, you can very readily unbind material which is, say, beyond about 10 AU from the star. So that's one of the things that makes photoevaporation potentially viable. The other thing is that these disks are optically thick to both the ultraviolet and the X-rays until you get down to column densities which would put you well into the debris disk phase. So protoplanetary disks are optically thick to these energetic radiation. And why this is important, it means that the flow conditions in the wind are being set in a heated layer which is high above the disk midplane. What that means, therefore, is that the rate of mass loss doesn't know about what's there at the midplane. You've got some sort of hydrostatic structure down below you which is feeding the heated region, but you're not directly heating the bulk of the mass reservoir. And why this is particularly important is that it means that as long as you remain optically thick, your mass loss rate from the disk doesn't change as the disk gets lower and lower in surface density, so as it drains. So unlike what we were saying just now about the jets, where the mass loss rate was related to the accretion rate, this should be a constant term throughout the lifetime of the disk. And therefore, whereas it can be completely insignificant at early times, there will come a time in the disk's evolution where this constant sink term would become comparable with the accretion rate onto the star. And that's the point at which it starts getting interesting. So, just very generically, if you have models for disk evolution and you combine it with a constant wind, then depending on the strength of your wind, you'll start off with the accretion rate as a function of time, just following your expected secular viscous power law decline. And then when the accretion rate drops to a point where it's comparable with the wind mass loss rate, it means that your disk is becoming starved of supply, because material which is trying to flow in is being removed in the wind, and at that point the accretion rate onto the star falls very rapidly. So you get these cut-offs at the point where these two accretion rates, where these two mass loss rates become comparable, and at what the strength of the wind determines at what evolutionary stage you get this cut-off. And many authors have looked into this type of behavior. I'll say a little bit about observational evidence for this. It's actually quite tough. There are a few things that have been looked for. So we're talking about energetic radiation, which produces free emission. And so there have been ideas of looking for free emission, which could be associated with a thermal wind above the disk. Likewise, gaseous flows can entrain dust from the disk, and so potentially give you, in an edge-on disk, a signature in terms of an entrained dust halo. And then there have been studies looking for evidence from emission lines from disk flows. And probably the best one at the moment is the Neon 2 line, which has got a low velocity component, about 10 kilometers a second. And this has been successfully modeled as being either due to X-ray photoevaporation or extreme ultraviolet photoevaporation. So there is some circumstantial evidence in terms of spectroscopy. But digging out evidence for these winds, which are at relatively low levels, is tough in the case of internal photoevaporation. As if I turn instead to external photoevaporation, so here this is where the radiation source is coming from neighbours in the cluster, so usually OB stars, you get something much more conspicuous, and these are the very well-known proplyds in Orion. And what you're looking at here is that each of these structures has a neighbour which is an OB star, and that both drives a neutral wind off the disk surface and then ionizes that wind at a finite distance from the disk, and that's why you see the bright rim which is offset from the disk surface. So this is a very obvious hallmark of external photoevaporation. Canonically, most proplyds that are known are in the Orion Nebula cluster, but recently we found some more around some rather lower mass stars in NGC 1977. So it's a great way of detecting a photoevaporative wind if you've got an ionizing source nearby which sort of shines a light on it. But of course, you can only do that in a relatively narrow range of environments. So we'll spend the next third of the talk talking a bit about internal photoevaporation, what we understand and what we don't understand. So just for starters, I'm going back to this idea that we're taking a wind mass loss model and connecting it with a viscous evolution model and looking at the secular evolution of the disk and wind system. So these are snapshots of the disk surface density profile in such a calculation. And initially, you have a self-similar decline of the surface density of the disk, so increasing time is going down the plot. And you start seeing the feature, which is the slight indentation just inside 10 AU, at the point when the accretion rate onto the star has dropped to being about the mass loss rate in the wind. Now remember, the wind can only drive from a bit further out in the disk where the temperature exceeds the local escape temperature, so the wind is being driven from around about 10 AU, so you can envisage material flowing in, but that instead of going onto the star, it's being caught up in the wind. So the slightly counterintuitive thing is it's actually the inner disk, which is the really securely bound part of the disk, which isn't going in the wind. That's the bit that actually disappears very quickly because it doesn't have any resupply. It's still accreting, and it goes onto the star, and you generate a hole. And then after that, the wind clears the residual disk from the inside out. And there have been many, many papers looking at the implications of this for disk demographics, and also for models of planet formation and planet migration, and also when you selectively remove gas and increase the dust-to-gas ratio, and what effect might that have on planet formation. There's a lot of work in this area. I'm not going to talk about that this afternoon, because I want to take a step back and say, how much do we, or should we, believe the underlying models this is based on? What is it we do understand, and can we say something analytically about it? And the answer is yes, we can. And also, is our understanding sufficient to really be able to say, I expect the photoevaporation rate in young stars to be X? And there you'll see that I come to a slightly more negative conclusion. So this is a topic which has been studied by many groups for many years, using a variety of treatments. Broadly speaking, all the models started off by doing the treatment of the radiative transfer and the thermal physics very carefully and beautifully, but not putting in hydrodynamics, which of course is a disadvantage if you want to get a wind flow rate out of it. So the advance from that was to start doing hydrodynamical modeling of the wind situation, where you can actually, in that sense, believe the mass loss rates better, but then it becomes computationally prohibitive to treat the radiative transfer and the thermochemistry at the same level of detail, so you make the economy of imposing a radiative equilibrium. And then that was already tractable 8 years ago. But more recently, there's been a new generation of models which relax the assumptions of radiative and chemical equilibrium, and therefore they also allow the possibility of cooling by PDV work. And this, again, would be computationally prohibitive if you didn't very much cut down the sophistication of your treatment of the thermochemistry. So when you say, which of these models are best, some of them are best at the thermochemistry, some of them are most reliable hydrodynamically. I'm going to say a few words about what understanding disk winds from an analytic perspective, because I think it's quite useful when looking at the results of hydrosimulations to boil it down, if possible, to some simple hydrodynamics. So anybody who studied fluids will remember that when you have flows which start subsonic and end up being supersonic, so say a spherical wind from a star, the familiar Parker wind solution, this solution passes through a critical point at some point, and the way this is usually expressed is you take the time-independent continuity and momentum equations, and if your gas was isothermal, which it isn't necessarily, but I just put the isothermal one there, you'd get a expression of this sort, and that's just an equation for the velocity if you know your gravitational field and your streamline geometry. Now the critical point comes in that there's one unique point where you go make a sonic transition, so the left-hand side has to be 0, and naturally you have to make sure that happens at the same point in the flow that the right-hand side is 0. And generally when you're doing wind solutions, that's the first thing you do, is you try and locate the critical point of the flow by ensuring that the left-hand and right-hand side of these equations go to 0 at the same point in the flow. And the Parker wind is the case of spherical divergence of an isothermal flow, say from a star, and that's achieved at a point where you balance the two terms on the right-hand side. That div dot s hat, that's the divergence of the unit streamline vector, so it's 2 over r for spherical divergence. So roughly speaking, you can say you go through a sonic transition at a radius where the sound speed is of order the escape velocity there. But on the other hand, there's another sort of class of these kinds of solutions where you can just, for example, take gravity away completely, and then you say the critical point is achieved at the point where the divergence of the streamline vector goes to 0. And so that's a nozzle solution, Duval nozzle. You take a pipe and you make it narrow and you flare it again, and the flow will go through its sonic transition at that point. And so which of these are we looking at when we look at a disk wind? Obviously, we're never going to completely get rid of gravity, but it could be that gravity is subdominant at the sonic surface. So I'm going to show, here are 2 simulations which are showing you what happens when you irradiate with X-rays and when you irradiate with extreme ultraviolet. So I'm talking about ultraviolet photons, which are just slightly more energetic than the hydrogen ionization limit. So I think at this point I may wield the fearsome stick here. What's plotted here on this red line here is the sonic surface. So it's the point in the flow where the flow velocity is equal to the local sound speed, and this is a color map in terms of temperature. So what happens is if you can read off this what the temperature is along the sonic surface, you can compare CS squared to GM over R, and in fact you find that the two are of comparable magnitude to one another. So it's saying it's sort of Parker wind-like because you're trading off those two terms at the sonic surface. Now, the EUV case is quite different. I mean, the color scales are a bit different, but if you actually look what it means, most of this material is at 10 to the 4 K rather than a few thousand K. It's here. It's a much hotter flow with ionized radiation. And so what's actually happening is if you ask what's the relationship between CS squared and GM over R along the sonic surface there, it's this dashed white line is the sonic surface, you actually find that the sound speed is much greater than GM over R, or in other words, the gravitational term is pretty irrelevant there. So that's suggesting that what's happening is that the flow is going through a nozzle at that point. And you can sort of look at those streamlines and maybe kind of convince yourself actually you do see a bit of pinching at that point. I'll come back to that in a minute. Now, both these insights allow you to say some analytic things about how these two photoevaporations work. So, firstly, in the X-ray case, if you've got irradiation of optically thin gas by X-rays, there's a well-known relationship between the temperature of the gas and the X-ray ionization parameter, which is just the ratio of the flux to the local number density. So this can be obtained from, say, Monte Carlo radiative transfer calculations or whatever, a relationship between this parameter psi and the temperature. But because we know it roughly satisfies the Parker wind criterion, so we know what the temperature has to be at every cylindrical radius, we need CS squared, roughly GM over R. We know at every point along this sonic surface what the temperature has to be, so we can read off here, and from that, if we know the X-ray luminosity and where you are in the disk, then you can find out what the local number density has to be for thermal equilibrium. And then you know everything that you need, because you know it's a sonic surface, so you know from the temperature how fast it's going, and you know the local number density. And so this is all rolled into this expression here. It's just saying analytically, once we know that it's behaving in a Parker wind-like manner, and we know the form of this relationship, we should be able to figure out, without doing any calculations, what the wind mass loss rate is through this integral. And the tick there means that it works in the sense that within a factor 2 or so, you can reproduce the mass loss rates that are found in simulations. So, of course, we don't know what's happening in reality, but it certainly means that that's exactly the way that the simulations are behaving. So it's always both gratifying and slightly annoying when there's been a lot of sort of PhD student years that have gone into doing a calculation, and then you discover that actually there's a very sort of simple way of looking at it. I actually think it's rather a good thing, because one wouldn't have got there without doing the simulation first. But what that means is that in principle, through this argument, as long as you know this function, which could, for example, change with the metallicity of the gas, then you can compile your integral and you get your mass loss rate, and save yourself a lot of bother in the process. So that's some sort of analytic insight into the way X-ray photoevaporation may be working. Can't do that with the EUV because it's virtually isothermal. It's 10 to the 4 throughout here. There's no special relationship between GM over R and CS squared. At the bottom of the ionization front, you are satisfying ionization balance along there, and this is a problem that was first of all worked on by Dave Hollenbach in the 1990s. We do know the run of density at the base of the ionized material, and then we just have to figure out the topology of the streamlines that lie above that. And we've made some progress on that recently from an analytical perspective as well. So a couple of years ago, Richard Alexander and myself found a new solution for isothermal winds in cylindrical symmetry. So this is actually a problem which has been around in all sorts of astronomical contexts for a long time, particularly in AGN. How do you write down the equations and behavior of streamlines of isothermal winds in AGN, for example? And what people have tended to do in the past is make up a streamline topology, and at that point it becomes fairly easy to figure out what is the variation of variables along that. But of course, in reality, the actual flow has to make up its own mind as to the shape of the streamlines. It should be self-consistently determined through the physics. So we actually managed to get a very compact similarity solution out for this, which is just contained in these small number of rather ugly-looking equations there. The gist of it is that the curvature of the streamlines everywhere is giving you the u dot grad u term, which balances the pressure gradient normal to the streamlines. The reason why we've been able to create a similarity solution is we've done something which is apparently very bizarre. We've actually forgotten about gravity and centrifugal force, which sounds like a very foolish thing to do in a disk wind where it's rotating at the bottom. The reason we did this is we got the idea by looking at numerical simulations and seeing that the results looked self-similar. They didn't look as though they knew much about a special radius equal to GM over CS squared. And so we tried this similarity solution, and then we compared it with the hydrodynamical simulations, which do, of course, have centrifugal effects and gravity in. And as you can see, the agreement is very good. Now, where you'd expect the agreement to be worse is where you're well down at very small radii, where the gravitational force is relatively strong. But even at 0.5 of a GM over CS squared, the solution is working well. And I think the fundamental reason is that it sounded like a crazy thing to do, but here you're in centrifugal balance, so gravity and centrifugal force cancel each other out. And then as you move out along the streamline, both of these decline, and they decline more quickly than the pressure terms and the convective derivative terms that we're retaining. So the bottom line from this is that it's now possible to calculate wind solutions within about sort of 20 seconds of CPU times, rather than having to do lots of bespoke radiation hydro calculations. And there are a number of applications. I spoke earlier about modeling lines and modeling entrained dust. It becomes a whole lot easier when you know your flow topology from the start. So there are two respects in which we understand things analytically better than we did, but let's get back to reality. Which of these is actually right? And so far I've talked about it from a very theoretical point of view, but probably what's more important is that the wind mass loss rates from these two different types of radiation are immensely different. It's about 100 times greater canonically from X-rays from EUV. The velocities are very different. It's a few kilometers a second for X-ray driven winds, and it's about 10 kilometers a second for EUV driven winds. So observationally, they should be very, very different. And then this is the sort of depressing bit of it, is that although I've introduced these as X-ray simulations and EUV simulations, both these simulations put in both EUV and X-rays. It's just that they end up discovering in each case that either one or the other radiation source turns out to be completely dominant and the other one is subdominant. So that probably cannot be right. That probably means that somebody is, or possibly both, are not treating something properly. But as I say, it's difficult because there's a lot that you need to get right to be sure of it. So I've listed here a whole bunch of things that probably need to be looked at in more detail. And my hunch would be that on the ones on the right, the EUV ones, they've had a relatively simplified treatment of the X-ray heating. They don't have many frequency bins, so that's something that could be improved. On the other hand, in the X-ray calculations here, there's no line cooling below a certain density. That's something which needs to be improved as well. So I think when the mist's clear on this one, there are the analytical tools there to understand it, but at the moment it's not quite clear which of these is actually going to be in reality. I mean, obviously in the end, if you happen to have a source which has a pathologically high X-ray luminosity and a very low EUV, you're pretty confident it will be on the left, and vice versa. But I don't think we've really got to the bottom of this yet, but it's something we're working on. So in the second half of the talk, I want to mention environmental effects. And although this is a talk mainly about photoevaporation, I want to ask, are interactions between protostellar disks and other stars in clustered environments ever important? And are they ever important at densities which are low enough that you're not swamped by photoevaporation anyway? Now, we do see some nice examples of where star-disk interactions are happening. One of the most beautiful of these, discovered a while ago by Sylvie Cadbury, was looking at RW Auriga, which has got a beautiful tidal tail. So RW Auriga is almost certainly a binary. It's a 200 AU separation pair of T-Tauri stars. It could, in principle, be a hyperbolic encounter, but the probability of having such a close encounter, given the low density of Taurus, is extremely small. So it probably is just a binary on an eccentric orbit. And a few years ago, we did some simulations to model as much as we could all the kinematic and spatial information that could have given rise to this kind of structure. And it is a pretty classic tidal interaction. Perhaps slightly more surprising is the case of HV and DO tau. So for those of you who are not T-Tauri specialists, these are stellar systems which are quite well separated in Taurus, about 10 to the 4 AU apart. Not much reason to believe that they had anything to do with one another in their origin. HV tau is a triple, and DO is apparently a single. But in the Herschel maps that were taken a few years ago, it was noticeable that they were enclosed by a common envelope which looked as though suggestively it had sort of tidal features. And you see the same thing in the scattered light images from the HST archive, which is down the bottom right. And scattered light, it looks like a pair of interacting galaxies. So this was the first projects that Andrew Winter did for his PhD, was to try and find out encounter histories using hydrodynamics SPH that would create something which is morphologically similar to what we see in the Herschel data, and again satisfy all the kinematic constraints that are there, including the recent things from Gaia DR2. And the solution he came up with was that these stars were once bound and had an encounter on a scale of a few hundred AU, and that it was the reconfiguration of the HV tau triple system which provided the energy to fling off DO tau into either an unbound or a very elliptical orbit. So yeah, these disks have definitely interacted with one another in the past. Now, I'd call that sort of behavior initial conditions. If you've seen one of the many simulations done, for example, by Matthew Bate or many others working in the field of star formation, you see one of the things that you get generically is small n-body groups in which you have a lot of interactions and reconfiguring of multiples. That to me seems to be a sort of an unavoidable initial condition for creating these disks. But there's also the question of, if you've got through this very early phase, and this simulations like this run for a few times 10 to the 5 years, your disks themselves live typically for many million years. Are they further pruned or dispersed if they're in a high density cluster? So remember, this origin's small clusterings could happen everywhere. It could happen in the solar neighborhood, it could happen in a globular cluster. That would, I'd say, is not environmentally dependent, but it's once you've got out of your little birth grouping, is there a significant attrition of disks by encounters? And I say, many people have looked at this, but they tend to only look at the dynamics and not compare with the photoevaporation that you'd expect in the environments that they invoke. So to do the calculation properly, you first had to improve how you model photoevaporation from far ultraviolet radiation. So just to be clear, it's an external source of FUV. We're talking about photons in the range of 6 to 13.6 electron volts. It creates a photodissociation region on the outside of the disk, and that drives a radial flow, so cylindrical radial, off the outer edge of the disk. There was a very nice paper in 2004 by Fred Adams and collaborators who took the results of PDR calculations. So here on the right, what you see is the temperature in a photodissociation region, so a region that's being illuminated with far ultraviolet radiation, as a function of AV, so optical depth into the slab, for different densities. I don't think you can see necessarily the screen very clearly there, but each of those lines there is a slab of a different density. So we've got a slightly complicated equation of state here in a PDR when we want to do the hydrodynamics, because our temperature is a function both of the local density and of the integrated AV, integrated outwards along the flow. So I just want to draw your attention before I change the slide to the fact that if you're optically thin, so you're at low AV, your temperature, of course, doesn't depend on AV. You wouldn't expect that, but it does still depend a lot on the density in these models. And this is something which turns out to be important. There's a rather grisly slide here. So this is what Stefano Facchini did in his thesis, and it was turned out to be technically quite challenging. This is an equation which is quite similar to the one I showed you earlier about the finding critical points. F is a temperature-like variable and G is a density-like variable. But the only point I wanted to make here, without getting into any grisly details, is that, as I said earlier, when you do a wind calculation, you always want to be able to find a critical point. And if you don't take into account the non-isothermal dependencies in the way that the temperature depends on things like local number density, you won't be able to locate your critical point. And if you can't locate your critical point, you can't find a solution. So that's what Fred Adams found. He presented a handful of solutions, but he didn't present many because he had ignored some of these terms in this equation. And it just turns out that they do turn out to be rather important in being able to locate the critical point. So in the end, that did work, and it meant that Stefano was able to generate a lot of wind solutions for a whole variety of parameters. And the way that we parameterize far ultraviolet flux is in terms of G0, so that's a Harbing field. It's relating the ultraviolet flux to its level in the solar neighborhood. At the bottom, there's just a histogram of the sort of environments that we believe that disks are born in, and this is the reason why there are lots of plots, lots of lines, is you can make various assumptions about the internal extinction within clusters. But the take-home message there is that this is a log scale, and it's got a big stretch on it. So disks are born in a very wide range of FUV environments, from the extremely strong to the very weak. So it was a great advantage that we could get a big range of analytical solutions out of this. So having done that, Tom Howarth had this Torus 3D PDR code. So that's basically a code that propagates the radiation to look at the local FUV flux density in every cell, then looks at the equilibrium chemistry and temperature that you get out given the local FUV field, feeds that back into the hydrodynamics, and then drives forward a hydrodynamic time step or a few hydrodynamic time steps, and then reevaluates. And it was very useful to be able to validate this code by having these 1D solutions that we had derived. But in fact, once we'd done that and validated it and debugged it, it turned out to be much easier in reality to go with the code for getting big model grids. And Tom's effort on this has just come to fruition. A few weeks ago, he produced this grid that he calls fried. It's 4,000 models of disks being irradiated by FUV fields of different strengths. And for example, this is a case of disks where you keep the same surface density normalization, but you cut them at different radii, and then you ask, what is the mass loss rate as a function of where you cut it, and as a function of the far ultraviolet field. And what you notice is that the rates are quite high. If we'd flip back to the accretion rates plot near the beginning, we were looking at accretion rates of 10 to the minus 8, 10 to the minus 9. So these are really quite competitive, even on scales of about 100 AU. So what does this mean? We now know, put a disk down in a given field of a given radius, we know the rate at which it's losing mass. How can we actually put that into real cluster environments and figure out what that means for their disks? So this is where Andrew Winter's work comes in, because he takes a bunch of disks which are viscously evolving, and as they say viscously expand, you can look up this library of mass loss rates and figure out the mass loss rate and evolve the whole system under the combined effects of photoevaporation and viscous evolution. So for example, in the plot up here on the right, for a bunch of different far ultraviolet fields, this one is starting with normal viscous expansion, so it's the outer disk radius, it goes out, but at some point it won't go out any further because the mass loss rate from the wind becomes too strong, and then it's driven inwards. So when you do these kind of calculations, you can ask simple questions like, if I want my disk to disappear within 3 million years, say, what sort of FUV field environment would I have to sit in? And it's also sort of rendered in this color plot here. 3 million years, you'd have to be at a G0 of around about 3,000. So that's something to bear in mind, and we'll come back into it in a moment. Remember, we're doing a comparative exercise of this with the effective encounters. So in this case, you're putting a disk of a given radius down into some stellar environment where you know its local velocity dispersion and you know its local density. And you need to use various prescriptions, which Andrew worked on a lot in his first paper, for working out the shrinkage of a disk as a result of encounters with various parameters, mass ratios, inclinations, eccentricities, etc. And then Monte Carlo sample the ensemble effect of all the encounters that you'd expect a star sitting in that environment to have over its lifetime, and then look at that population and figure out what is the effect in shrinking a disk on the fact that it's sitting in a stellar environment. And forget about the green for now. The black line is showing if you start off with a 100 AU disk, you really do very little to its outer radius. The mean of the distribution hardly changes. The median does change a bit for this density. I've taken a high density. This is getting on towards the core of the Orion nebula cluster. And the effect of encounters is to reduce the median radius from about 100 to about just below 90. This is a very mild effect compared with what we were seeing for FUV in the previous slide, by the way, in the sense that there we were seeing that on those sorts of timescales for the higher G0s, we were taking our disks down to 10 AU and getting down to about 10 to the minus 6 of a solar mass of gas left. So already we're getting the sense that photoevaporation is more brutal for disks than encounters. But to quantify that, you actually have to look at where real clusters lie. So this is quite a busy plot, but it's almost the last thing I show you, so it's worthwhile just thinking about a moment. It's getting compiled by Andrew. So it's a plot of G0, so that's strength of the far ultraviolet field, and this is the local stellar density. And what he's done is to estimate for any given cluster, say the Orion Nebula cluster, as a function of radius within the cluster where it lies in this plane. So obviously you have to make assumptions about the IMF and the spatial distribution of massive stars and that sort of thing to compile such a plot. It's unsurprising that these are positively correlated. There's quite a spread here, but nevertheless a general trend, sort of a locus in which most clusters seem to lie along. So just to emphasize, any one cluster is smeared out as a line along here from its core up this end to its outer reaches down there. And then we just put on this diagram the places where we say that there's a 3 million year destruction time scale, but actually we've been very kind to encounters by asking for, when we say a tidal time of 3 million years, we're defining that as a shrinkage only from 100 to 80 AU, whereas when we put in our criterion for destroying by photoevaporation in 3 million years, we're actually making a much more stringent criterion in terms of what happens to the disk. So the reason why we're not being sort of worrying too much about being level between these two things is that the point is that where there's a choice between which is the important process, photoevaporation just about always wins, even when we bend over backwards to make the encounters more important. And it's only right up here in some of the more familiar exotic environments near the galactic center where encounters become important as well as photoevaporation. So if there's any take-home message, I think it is that we should be worrying in general much more about the influence of photoevaporation than encounters. What's the evidence for all this? A paper came out a few years ago which probably hasn't had as much attention as I think it probably deserves. It's down here. It was looking at the Cygnus OB2 OB association, picking out the low mass stars there in the X-ray, and then so identifying them as young low mass stars, and then looking for the fraction of them that had near infrared excess, that had disks, and then drawing a map on the sky of what the estimated G0 value was experienced by the stars. So obviously you don't know the 3D projections, but you know where the OB star's in here, so you can estimate for every star what's the local G0 it's in. And then in this histogram, this is the disk fraction as a function of where it lies as a function of G0. And I think this is really pretty convincing evidence that there's a depletion of disks towards high G0 compared with low G0. You can't really see the scale here. We're going from about G0 of 1,000 to about 3 or 4 times, 4 times 10 to the 4 up here. And so Andrew's most recent project is to say, well, can I actually make Cygnus OB2 in a dynamical sense, starting from fractal initial conditions, removing a gas potential, and creating something which looks like Cygnus OB2 spatially, which has got the right sort of proper motions, and which can also reproduce the correlations between apparent local FUV flux and disk fraction. And the way you do that, it is quite laborious, and you've got your n-body model, which gives you trajectories for every star, and then every star has got a little viscous evolution code, if you like, attached to it, which iterates the viscous evolution of the disk and has to know what the local G0 field is, because of course that will change during the dynamical evolution of the cluster. So it's an effort really of going towards constraining cluster histories, not only using the things that we think about most readily, but also throwing in the extra information about the effect of environmental destruction. So I put my conclusions up here. I don't think I have to read them. Those were the take-home messages. So thanks very much for your attention.